You've all seen the periodic table, right? But what if I told you it's not just some chart you had to memorize in school? It's more like a map, a kind of cheat sheet with a hidden code that predicts exactly how every element in the universe is going to behave. Today, we're going to crack that code. And we're going to start with a puzzle that, when you first hear it, seems to make absolutely no sense. It's all about how big these atoms actually are. Okay, so as you move from left to right across a row on the table, you're packing in more stuff, more protons, more electrons. The atoms are getting heavier, which makes sense. But here's the paradox. They also get smaller. How is that even possible? More stuff should mean bigger, right? And this isn't just a fluke. It's a real, predictable pattern you see across the entire table. The atomic radius just keeps on shrinking as you move across a row. But you know what? This isn't the only pattern hiding in plain sight. Take a look at this graph right here. This shows something called ionization energy, which is basically how much effort it takes to steal an electron from an atom. See that repeating up and down, peak and valley pattern? That's the code at work again. And if we can understand why these trends happen, we pretty much unlock the secrets to all of chemistry. To solve this mystery, we have to zoom way, way in, right inside the atom itself. Because in there is a constant, epic battle being fought for control. It's a fundamental tug of war. On one side, you've got the super powerful positive charge of the nucleus, and it's pulling all those negative electrons inward. But on the other side, you have the inner electrons basically pushing the outer electrons away. That repulsion, that push, is called shielding. You know, a great way to picture this is with magnets. Imagine the nucleus is a really strong magnet trying to pull in a little metal ball. That's our outermost electron. But there are other metal balls, the inner electrons, right in between them. They get in the way. They shield some of that magnetic force, making the pull weaker. So you've got this pull of attraction versus the push of shielding. Who wins this tug of war? Well, the outcome of this whole battle and the secret to all those trends we saw, it all comes down to one single, incredibly important concept. And that concept is called effective nuclear charge, or ZF for short. Now, this isn't the total charge of the nucleus. No, it's the net charge, the actual pull that an outer electron really feels after you subtract that shielding effect from the inner electrons. Honestly, this is the master key to everything. Let's see it in action. If we go across the second row, from lithium over to fluorine, we keep adding protons, but here's the key. The outer electrons are all in the same energy shell. That means the number of inner shielding electrons doesn't change. So what happens? The effective nuclear charge, that net pull, just skyrockets. And these numbers really tell the story. An outer electron in fluorine feels a net pull of plus 5.10. Now, compare that to lithium's tiny 1.28. That is a huge increase in the inward force. The magnet just got way, way stronger. Okay, so now that we have our secret weapon, ZF, we can finally go back and solve that weird paradox about atomic size we started with. And there it is. Mystery solved. The reason atoms get smaller as you go across a row is because that dramatically increasing effective nuclear charge just wins the tug of war. That stronger pull literally reels in the entire cloud of electrons, squeezing the atom tighter and tighter into a smaller radius. But what about going down a column? Well, here it's a completely different story. Every step you take down adds a whole new shell of electrons. So not only is this new shell physically farther away from the nucleus, but it's also being shielded by all those new layers of electrons underneath it. Both of those things weaken the nucleus's pull. So the atoms get much, much bigger. And what's so cool is that this one concept, effective nuclear charge, doesn't just explain size. It also explains why some elements are super greedy and hold on to their electrons for dear life, while others are just happy to give them away. It all just connects so perfectly. Think about it. If an atom has a high ZF, its nucleus has a death grip on its outer electrons. That means you need to use a ton of energy to pull one off. That's your high ionization energy. And it also means that same nucleus is fantastic at attracting other electrons in a chemical bond, and that's high electronegativity. And this explains the extremes. It's exactly why fluorine, up in the top right, with its tiny size and massive ZF, is the undisputed champion of attracting electrons. And it's why francium, way down in the bottom left, with its enormous size and heavily shielded outer electron, can barely hold on to it at all. Okay, now let's look at a really fascinating case that shows just how powerful these rules are, especially when things get a little weird.
This is the story of what happens when electron shielding just doesn't do its job properly. So, up until now, we've kind of been assuming that shielding works pretty well, but the shape of the electron orbitals really matters. Some orbitals are great at shielding, but others, well, they're terrible at it. So, what happens when you have a whole group of electrons that are just really bad at their one job?
Well, you get this incredible phenomenon called the lanthanide contraction. As we move across that weird little row at the bottom of the table, the lanthanides, we're filling up these f orbitals. And these f electrons are absolutely terrible at shielding. So the nucleus's charge grows and grows, but the shielding barely keeps up. The result? The atoms shrink way more than you'd ever expect. Now, the real-world result of this is just stunning. Look at these two elements, zirconium and hafnium. Hafnium has 32 more protons. That's a huge jump in nuclear charge. But because it comes right after the lanthanides, that contraction has pulled its electron shells in so incredibly tightly that it ends up being almost the exact same size as zirconium. It's wild. And this makes them chemical twins. Their properties are so similar that they're almost always found together in nature, and they are notoriously hard to separate from each other. It's just a perfect example of how these invisible forces of attraction and shielding literally dictate an element's entire identity. So the next time you look at a periodic table, don't just see a grid of boxes. See it for what it truly is, a beautiful, elegant, visual map of that constant tug-of-war that's happening inside every single atom in the universe. And that kind of leaves us with one last big thought. We've just seen how two simple, competing forces, attraction and shielding, give rise to the entire, incredible, complex world of chemistry. It really makes you wonder, doesn't it? What other simple, elegant rules are out there, quietly shaping the complexity of the universe all around us?